Hi everyone, this is VK. Welcome to Smid World. Here I am with another video. Gearboxes service, maintenance and condition. We will see in this video the topics were selection, operation and maintenance, mechanical transmissions in use of centuries for transmit power and motion. The unique machine element finds use of mathematics, engineering, metallurgy, etc. to achieve operational reliability. Operation reliability involves speaking the truth between two entities, the full and frank, that is, to speak the truth. In these main topics are failure analysis, gear contact patterns, gear damage, pitting, initial pitting, destructive pitting, secondary pitting, spalling, scoring, cracks, grinding cracks, tooth breakage, overload breakage, fatigue failure, frosting, that means gray staining, bearing failure, primary damage, secondary damage, and finally lubrication. Basic criteria for a proper selection of gear units are mechanical rating, thermal rating, bearing lifetime, type of lubrication, special requirements, and other accessories. Selection as per mechanical rating, required data, type of prime mover, type of driven machine, daily service, and duty condition, that is in hours per day, motor power in kilowatts, motor speed in rpm, output speed rpm, the service factor, and starts per hour, actual or effective output power in kilowatts, relative position of input or output shafts, handling of gear units. Selections as per thermal rating, required data, ambient conditions, open space, small or large premises, ambient temperature in degrees centigrades, minimum and maximum, operating cycles per hour in percentage, wind velocity. Gearbox selected to be vetted for thermal rating whether natural cooling is sufficient to take care of heat generated. If not, one of the following cooling to be incorporated: the fan cooling, cooling by fan and cooling coil, or pressure lubricant system with external cooler. Types of lubricant: normally mineral based oil of 320 or 460 viscosity at 40 degrees centigrade. For splash lubrication, 460 Vg viscosity oil, or pressure lubrication, 320. Excess oil leads to churning losses and higher temperature with added pressure on seals. Ideally, temperature to be restricted to 90 degrees centigrade while safe till 95 degrees centigrade, failing which oil life drastically reduces. For every 10 degree above, 65 degree oil life becomes off. Unforeseen load or force and external vibration, if not taken care while selection, sudden failure partially or wholly. Improper mounting and commissioning will also lead to failures. Under noted hints will help avoiding unnecessary failure. Correct mounting and commissioning of gear unit with the coupling, etc. Proper selection of quality and quantity of lubricant. Oil change as recommended. Regular checks of seals, lubricant, temperature, noise and vibration. Note: if additional cooling is restricted because of site condition, higher size of gear unit to be selected, or use two fans or special fan with proper air guide covers, or increase the surface area of gear housing. Lubrication: depending on circumferential speed, lubrication is chosen. Circumferential speed of pitch circle lesser than 15 meters per second is equal to splash. Circumferential speed of pitch circle greater than 15 meters per second equal to means it's a pressurized lubrication. Note: forced lubrication system mostly is a combination of splash and pressure. Tooth correction, profile correction, longitudinal correction. Correction to remove localized load increase due to deformation under load. The series designed is how to find nomenclature by seeing the nameplate. helical bevel, E for single, Z for double, T for triple, V for quadruple stage, and N for solid shaft, A for hollow shaft, O for hollow shaft torque. Last one, last stage and last two sizes 1 to 26. Development of design over the years. Torque 23,800 meters. Past tendency prevailing in industry with respect to gearing reverse, rise power levels to an ever increasing extent while decreasing physical sizes and using less weight. Improvements were developed by changing tooth profile, using higher quality materials, upgrading surface finish, hobbing with protuberance, using effective heat treatment process, using other types of lubricants and so on. In spite of improvements, the damage may occur as a result of faulty design, selection of improper material, use of improper materials in the mating gears, manufacturing errors, heat treatment errors, assembling errors, changing or unknown operational conditions of foreign parts or particles, use of improper lubricants, and so on. Rarely, only one of the above mentioned reasons accounts for the generation of damage to gear units. Assessment of damage in gearing requires in-depth knowledge of gear contact pattern, gear tooth failure modes, and lubricant systems and all. Gear contact patterns. Faulty contact patterns develop when load applied on only one end of the tooth crank causes due failure in manufacturing and failure during assembly, adverse effect during operation. Manufacturing errors mostly arise due to flank alignment errors due to manufacture, errors in housing machining. They appear in the form of axis inclination of deviation errors. Installation errors generally arise due to lack of proper alignment or adjustment. Adverse effects in operation mostly involve alignment errors, tension load, or vibrations. Contact pattern, you can see here, only part of the tooth flank worn out, matching tooth contact. Bearing damage. In machines, they are among the most important components. Heavy demands imposed on the load bearing capacity and as a result continue to be subject of intensive R&D. Research and development allows calculation of bearing life to a high degree of accuracy. Cases may still exist of premature failure. Reasons can be numerous such as unpredictable overloads, inadequate or ineffective lubrication, improper handling, high interference, etc., is lack of bearing clearance. Any of these factors results in its own typical failure, reflecting in a characteristic failure pattern on the bearing. Consequently, it is feasible at an early stage to identify the failure cause and take appropriate measures to avoid recurrence. Primary damage such as wear, indentations, corrosion, etc. is the start of secondary damage leading to peeling and cracks. Presence of primary damage may render it as a scrap, for example, excessive clearance, severe vibrations, or noisy running. Often failures reflect primary and secondary damage, where in normal circumstances wear will not be observed in anti-friction bearings. Wear may, however, occur if foreign particles enter the bearing or lubrication is inadequate. Wear caused by a foreign particle. Figure 2, wear inner ring of cylindrical roller bearing. Indentation caused to races and rollers when external forces applied for foreign material extended the bearing. Erosion occurs where water or aggressive media enter the bearing so that the lubricant can no longer preserve the steel surfaces effectively. Current flow. When current flow through a bearing, an effect similar to electric arc welding can be produced at the transition points. Also, often rippling is caused in the races and rolling element. The rippling on the outer ring of the spherical roller bearing due to current flow. You can see in picture clearly the current flow in the outer ring of the spherical roller bearing. Peeling is a result of normal fatigue when bearing is near the end of its useful life. The condition is indicative due to generation of more noise and vibration. Premature peeling can be due to inadmissible loads or corrosion, current flow or smearing. Progressive stages of peeling section. Peeling action. Peeling on the inner ring and rollers of taper roller bearing causes wear, excessive load and lack of proper lubrication. Peeling on the inner ring of a spherical roller bearing, ratio of axial to radial load is very high. Cracks. Cracks can be result of impact loading of the bearing during installation. Visual appearance. Cracks of or metal fragments broken away as a rule on one side of bearing ring. Forged close with a hammer or hardened manual against the bearing ring during installation. Action. Always use soft manual or fitting sleeve for installation. The bearing ring broken in the transverse direction and is floating on the shaft. Using too much force in the pressing the bearing on the capper seat. The follow supplier installation or instruction. The secondary damage, the cracked outer wing in a spherical roller bearing showing indentations at the lower rim of the race due to improper handling. Cracked inner ring of a spherical roller bearing. Cracked inner ring of spherical roller bearing broke due to seaming effect. Bearing handlings, do's and don't do's. Kinematic viscosity millimeter square per second is mostly accepted. The grade comprises a range with midpoint viscosity plus or minus 10%, that is Vg 320 covers the range 288 to 352 at 40 degrees centigrade. The viscosity groups generally used are Vg 220, 320, 460. The functional requirements: reduce coefficient of the friction in tooth mesh and anti-friction bearings. Disperse thermal energy from friction points within the gearbox to housing walls, thus atmosphere. Properties and benefits: high wear protection, benefits extended gear life, neutral towards micro pitting, extended gear life, high corrosion protection, extended gear life, excellent oxidation stability, long oil life, excellent deposit control means long bearing life. Excellent anti-foaming properties means negligible waste at sealings. High multi-material compatibility means longer life of other items. Advantages, disadvantages of lubrication: higher the viscosity, thicker the oil film between the two flanks, higher wear resistance, better grease staining capacity, improved bearing life, improved noise damping. Poor flow, higher churning losses. Limits: kinematic viscosity 50,000 millimeters square per second or will not flow satisfactorily. For pumps at 1500 rpm, permissible viscosity should be less than 5000 millimeters square per second. Kinematic viscosity below 25 millimeters square per second will not ensure load carrying property. Oil film becomes too thin. The influence of temperature on viscosity on metal. Scuffing capacity. Bearing load means that scuffing failure during load is only just avoided. The scuffing capacity of an oil is determined by the FZG test. During test, load is increased from stage to stage according to precise specifications in a standardized gear unit. Wear material is weighed repeatedly at given time intervals. At a point where tooth wear increase abruptly, the scuffing capacity will have come to an end. Suitability of the oil for the minimum load stage 12 plus. The gray staining capacity. The bearing load means that gray staining during load is only just avoided. A standardized methodology does not exist to ascertain when the gray staining will occur. Main influences are additive combination in oil and tooth flank roughness. Performance of the test. Life. Mineral oils produced from crude oil. Here comes the synthetic oil. metal oil. The comparison you can see here.